Welcome back, everybody. Today we're taking a look at matter, substances versus mixtures. And at this point, you should have already gone through the lecture notes, and you've actually done the lab with like the little columns where I gave you the specific examples and we cut them out and set them in. And what we're going to do today is just start to look at this in a little bit more detail. So, a quick review, right? We said that matter is just something that has mass and volume. In other words, it's something that exists. We can then further categorize what type of matter would it be by breaking it into these main two categories of, is it a pure substance or is it a mixture? So pure substance, it's just going to be something that's like chemically bonded. We could either break it down into an atom of just one thing, or it would be something that's chemically bonded. We can't physically separate it. If we're looking at a sample of matter and we say, no, it's not on the periodic table of elements, it's not something we could break down to just one atom, it's not something that's chemically bonded, I could actually separate these by some sort of a physical means, then it's going to be a mixture. And the mixtures could get broken down into a homogeneous mixture where everything's the same all the way throughout. If I sample it from the top, the bottom, the middle, it should look exactly the same. Or it's going to be a heterogeneous or a different type of mixture where you can actually like see where the differences are. So this first example that I've gone through for you here, we've got our samples, and then we first got to decide which of these two main branches does it go under, and then we can further categorize it into one of the bottom guys there. Technically, this is a diatomic molecule, but I just have chlorine. I'm not sure how familiar you are with the periodic table at this point, but we're going to keep things simple to get through this first unit of Chem A and just say, look, if it's on the periodic table of elements, let's just call it an element. But before we do that, right, we've had to say, all right, chlorine, I could break that down to just one thing. Even though this guy's kind of bonded together, we're going to say, okay, well, this is pure substance, and I'm going to call it an element. And again, this is probably a goofy example here where I could have got more specific, but let's move on here. So I got water. Check this out. The hydrogen and oxygen, right? It's chemically bonded. So you might think, well, yeah, that's a mix of some hydrogen and some oxygen, and you'd be correct. But if I try to separate that hydrogen from that oxygen, I can't do it with like a physical means. I can't just like boil off the hydrogen or filter off the oxygen. I'd have to use some sort of a chemical separation or electrical process. So we're going to say, okay, this is bonded chemically, so it's a pure substance, and we're going to just call this a compound. Soil, dirt. If you went out to your backyard with a shovel and you took one big shovelful and plopped it down on your desk, would it look the same all the way throughout? Is soil something that's found on the periodic table? No. Is it something that you can't separate physically? No. So we're over here, right? We know that soil's got to be an example of a mixture. Now, would I expect every single sample that I took from that shovelful to look the exact same? I mean, I might find a worm, I might find a little branch or some roots or some grass or some rock. That's not going to be the same in every single sample. So that would mean, yeah, it's a mixture that's different. And that would make it a heterogeneous mixture. Here's one where you might be a little confused, right? Because you might say, okay, well, look, we were up here and this stuff was chemically bonded. So we said that that was a compound, right? Well, check this out. This is sugar water. So we've got sugar here and water there. So it turns out that sugar water is a mix of water and sugar. Now, if we just had sugar, compound. If we just had water, compound. But we've got sugar water. You may be asking yourself, okay, Cash, you said mixtures could be separated. How the heck would I separate sugar water? Well, if you had a real good filter, you could do that. Or if we wanted to boil off the water and then, collect that evaporation, and then we'd be left behind with the sugar, that would be a way we could separate it. But there are ways that we could do it. So now if I had my sample of sugar water, would I see the sugar floating in it? No. I mean, if you reach what's called, saturation, you might see sugar on the bottom, but we're going to assume that that's not the point. So if I've got these two here, I would think that the samples would be the same throughout, and I'm going to call that a homogeneous mixture. Oxygen. Kind of in the same little bugaboo where this guy's a diatomic one and we haven't discussed that yet. But let's just say, you know what? I know oxygen is a pure substance found on the periodic table of elements. And for now, we'll just say oxygen's an element, and I think that'll be good. We've got carbon dioxide. Okay, CO2. Chemical bond there, right? So this would be an example of a pure substance. Oops, I guess I probably could have put pure substance for all these guys too, huh? This is a pure substance. It's not just an element, so we're going to call this guy a compound. Rocky Road ice cream. Num, num, num. So is that something I could break down into just an atom? Yeah, there's a lot of stuff going on there, but so much that this is actually a mixture. And I know that every single spoonful I get of this ice cream, it's not going to be the exact same, right? There's going to be some chunks of different things in different spoonfuls, and that adds to the fun and deliciousness. But nonetheless, that is a heterogeneous mixture. Alcohol. I see that these guys are all chemically bonded. So it's going to be a pure substance. And this is not one element, it's a bunch that are chemically bonded. So we'll call that a compound. Pure air. Oof, look at all this stuff. And erroneously, a lot of times kids will think, hey, air, sure, it's mostly oxygen. No, no, no. It's actually mostly nitrogen, which is a good thing. Oxygen is flammable. We'd be like engulfed in flames if the oxygen was the bulk of a breathable air. But this is also mixed up well enough to where, I don't have to worry about jumping from a pocket of nitrogen back into oxygen. Stay away from the CO2. Look out for the argon. So this is going to be so well mixed up that all samples are the same, and air would be an example of a homogeneous mixture. Iron, Fe, kind of a goofy one. That's the symbol for iron, and I know a lot of times kids would think like, well, man, Fe, there's no F or E in iron. Why the heck would that be the symbol for iron? Well, it's a pure substance, and that's an element. And reason being is you got to remember a lot of these elements, they were discovered in languages other than English. So ferrium is iron in Latin, and that's where that comes from there. So hopefully you're at a spot where most of these you could categorize well, or at least you can kind of see the logic of where I came up with this. So if you flip this guy over, got a little bit of a different scenario here, right? We've got some visuals. And I'm looking at this, and it doesn't even really matter so much what this stuff is, right? I've got white circles, black circles, just white circles. White and black circles appear to be bonded here. I look down to see, excuse me, I've got white guy, black guys here that are kind of bonded, separate little black circle, separate little white circle. White circles bonded, and then some separate ones. So if we take a look at this, we've got to decide, is this going to be, an element, or is it going to be a compound, or is it going to be a mixture? So in question 1 here, it says, which box contains only elements? So an element's something that you could break down to just one atom. And I'm looking at this, and if it's just elements, it looks like we've got some bonds there, right? Got some bonds of 2 different guys for sure there. You've got different guys that are kind of bonded there. So I'm going to go B. Now, this is, again, where we could probably say, well, look, these here are all the same, even though some of these are kind of bonded, those diatomic molecules and those atoms that are solo. So if you included D up there for where we're at right now, that'd be okay. But I'm just going to go with B on this. 2, which box contains only compounds? So that's going to be ones that are chemically bonded. Well, we just said this is an element, so it can't be that. I look at this, box A, everything appears to be chemically bonded. So I'm going to say, well, A. And notice that here it says which box contains only compounds. So I've got some solo guys here. These are solo atoms or solo elements. That's what they're supposed to represent. So that can't be that. And then, if I look back at this guy, there's those solo guys again. So that can't be that. Compounds are something that's like chemically bonded. And it looks like they're showing that with circles that are kind of stuck together. So which boxes are mixtures? So a mixture is going to be where, again, I can't break it all down to just one thing. That's an element. It's a pure substance. I've got these guys. These are compounds, right? If you notice all these ones, they're chemically bonded. I can't physically separate those. But if I look at this, different stuff. So C is going to be one. And if I look at this, I'm going to say, look, these guys and those guys, they're different things. I could probably separate those out somehow. So I'm going to say C and D. Now we're getting down to a little bit more of the same, right? But we're really got a bit simpler of a path here because we're just saying, is it an element or compound? So these guys are our pure substances, right? They're going to be the ones that you can't physically separate. Or is it just a mixture? So this does not mention, is it homogeneous or heterogeneous? So let's see what we got. Sodium, another one of those little goofballs that's got a weird symbol for what sodium actually is. It's an element. Water is our compound. These should look kind of familiar. Look at all this stuff that's kind of added up. Your tap water is actually a mixture. There's fluoride in there, so it's good for your teeth. And then you might have some calcium and some sodium or some other elements. A lot of the bottled waters puts that in there for taste. But nonetheless, that's a mixture. Coffee, well, it's definitely not an element or a compound. It's a mix of stuff. And we don't need to say, is this a heterogeneous mixture or not? But, turns out this guys would both be homogeneous mixtures. But that's not what we're asked here, right? Oxygen, I'm going to call that just an element, even though it's one of those diatomic guys with a 2 there. Alcohol, got all these elements chemically bonded. So it's going to be a compound. Chemically bonded, compound. Cake batter, oof, if you've ever baked before, right? There's a lot of things that you're mixing in there. We're not asked if it's homogeneous or heterogeneous, but if it's mixed well, it should be homogeneous. Air looks familiar, right? Remember, got a mix of all this different stuff. So that's going to be a mixture. Soap is a mixture. Lead symbol is Pb. That is an element. Jumping over to our final column here. Check this out, man. We're in the home stretch. Salt, water. Could I separate these? Yes. So I could physically separate them by boiling or filtering or whatever. Ice cream is also a mixture. Diatomic guy, but that's an element. Nitrogen is. Eggs. Mixture. A lot of stuff going on in there, right? Blood. Mixture. Table salt. This and this, by which I mean sodium and chlorine, sodium chloride. Those guys are chemically bonded, so we're going to call that a compound. A lot of stuff going on with nail polish. That'd be a mixture, as with milk and cola. And orange juice. Helium, I could find that on the periodic table. And methane, I could find that and that on the periodic table, but they're chemically bonded to form this gas, and that would make that a compound. So hopefully you're at least at a spot where even if you couldn't just race right through this, if you hear the explanations, it's starting to gel. If you have any questions, let me know. And if not, I'll see you soon. Bye-bye.